In this video, we will look at a few electricity problems. These are problems on the concepts associated with electricity and circuits. Problem 1. An electric current is given by this expression. So what this expression means is that the electric current is a function of time, and that mathematical function is given by that sine function. So I is in amperes, that's the current, and T is measured in seconds. What is the total charge carried by the current from 0 second to 1 over 120 seconds? So of course, to solve this problem, we have to make use of the definition for electric current, which is quite simply the rate of change of charge in Coulomb. So this equation can be rewritten slightly in integral form in a following manner. dq dt dt. So the right hand side of this equation will simply becomes dq, or integral of dq. Now note that this is quite simply the same equation that we have rewritten over there. Now let's substitute the expression for that current function, namely that function right there. So 100 can be taken out because it is simply a constant. Sine 120 pi t dt. Now the time, or the limit for the integral, goes from 0 to 1 over 120. So at t equals to 0, the zero charge, and at the end of the time interval, an amount of charge q would have passed through. So the left-hand side of this equation is quite simply q. Q is what we want to determine. And let's solve this integral now. 100, when you integrate sine function, you will have a minus cosine function. Now do not forget about the constant, so the constant will go in the denominator like that, minus cosine 120 pi t, and the limits are 0 to 1 over 120. Now let's substitute the limits. So substituting the upper limit first, you have minus cosine 120 pi 1 over 120. So that is the upper limit, minus cosine 0. So this 0 is the lower limit. So as you can see, this is going to give you 10 over 12 pi. The 120 and 120 will go away, so that's going to give you minus cosine pi plus 1, because cosine 0 is 1, minus minus is this plus. Since cosine pi is minus 1, so the entire term in the bracket is quite simply 2. So you see that this charge for that time interval will simply become 5 over 3 pi Coulomb, or quite simply 0.53 Coulomb. And that solves the problem. Problem 2. In the circuit below, the maximum power that can be safely delivered to any one of the resistor is 50 watts. What is the maximum voltage that can be applied to the terminals A, B? For the voltage determined in part A, what is the power delivered to each resistor? Let's simplify the circuit a little bit. So this is the 200 ohm resistor, and we can combine this and this using the parallel rule, and that's going to give you 100 ohm as the equivalent resistance. So this is point A and this is point B. Now we want to determine the maximum voltage that can be applied between A and B. Let's assume the current that results is IM. When you apply Vmax as the potential difference between A and B, IM is the current that results, that goes from here to there. We know that the maximum power that can be delivered to any one of those 200 ohm resistor is 50 watts. So the power delivered to this 200 ohm resistor is 50 watts. Note, the expression for power is I squared R. So that means since the same amount of current also goes through the 100 ohm resistor, the power delivered to the 100 ohm resistor has to be half, which is 25 watts. So now note that if we reduce the circuit further into a circuit with just one resistor, namely 300 ohm resistor, as a result of combining 200 and 100 ohm resistors in series, so that's point A and point B, the potential difference is the same Vmax that we want determined, and the current is IM. The power delivered we know is 75 watts. We can use this information to determine Vmax. Note, another expression for power is the potential difference squared over resistance. So in this case, the power is 75 watts. The potential difference is what you want to determine, Vmax, so square that, over the total resistance is 300 ohms. And you end up with the answer for Vmax as 150 volts. So that is the answer for part A. To get the answers for part B, we need to know what IM is, the current through the circuit. Now, using Ohm's law, we know that Vmax equals IM times the total resistance, which in this case is 300. Now, Vmax is 150, so IM is quite simply half ampere. So that is the current IM. So note, IM is the current through the 200 ohm here, and we know that's half ampere, and it's going to split equally because here you have equal amount of resistance. So here it's going to be 1 over 4 ampere and 1 over 4 ampere. So the power delivered to this 200 ohm resistor is quite simply IM squared R. So IM is half, square that is 1/4, times 200. And that's going to be 50 watts. Now power delivered to this resistor and that resistor can be computed in a similar way. They must be the same because the current through them is 1 over 4 amperes, square that, times the resistance, which is 200 ohms. And that's going to be 12.5 watts. And that completes the problem. Problem 3. Determine the current in 2 ohm resistor. So that is this resistor right there. And what is the potential difference between points A and B? So let's label the potential currents. So current that's coming out from the 12 volt battery, let's label that as I. And current through that part of the circuit, let's call it I1. And then eventually the current that gets to the 2 ohm resistor, let's call it I2. So the current through the 6 ohm resistor is quite simply the same as I1. And the current through this 4 ohm resistor is quite simply I. So let's write down the junction rule for this junction. The junction rule states I, the current towards the junction, is the same as the sum of all the currents that's leaving the junction. In this case is I1 plus I2. So that is equation 1. Next, let's look at loop rule through that loop in that direction. Note, let's start from the battery. As you go around the loop, you will go through the battery in that direction. So that's going to pick up a plus 12. Next, when you get to the 2 ohm resistor, you will go in the same direction, in the direction of the current. So that's going to pick up a negative term for the potential difference. So it's minus I2 times 2. And finally, as you close the loop, you will have to go through the 4 ohm resistor in the same direction as the direction of the current I, and that will give you another negative term for the potential difference, I times 4. And that's it, only 3 terms, and they all should sum to 0. That's the loop rule. Now let's rewrite this equation, and that's going to be I2 plus 2I equals 6. So that's equation 2. Note we have 3 variables, I, I1, and I2, so we need 3 equations to solve for these variables. So that means we need one more loop, and let's look at that loop, traversing in that direction. So first we go through the battery in that direction, so that's going to pick up a plus 8. Next, you're going to go through this 6 ohm resistor in the same direction as the direction of the I1 current. That's going to give you a negative term for the potential difference, I1 times 6. And finally, you will go through the 2 ohm resistor in an opposite direction as the direction of the I2 current, and that's going to give you a plus term for the potential difference across that resistor, I2 times 2, and there aren't any other components left in the loop, so they all should sum to 0. Rewriting this equation, we get I2 minus 3I1 equals minus 4. So that's equation 3. Solving for these 3 unknowns from these 3 equations, we will get the following solutions for the currents. I equals 2.545 ampere. I1 is 1.636 ampere, and I2, which is the current that we are looking for, is 0.909 ampere. So this, the third number, is the answer for the first part of this problem, which is the current in the 2 ohm resistor. Now let's look at the potential difference between points A and B. Now A and B, the direction from A and B does not form a closed loop. So note that in general the direction of the current is going from A to B. So to compute the potential difference between points B and A, we need to sum up all the contributions in between. So you have 2 contributions, one is the battery and the other one is the 6 ohm resistor. So now note that as you go from A to B, you are going through the battery from the negative to the positive terminal. So that's going to contribute a plus 8 term. Next, the 6 ohm resistor, you are going across the resistor in the same direction as the direction of the I1 current. So that's going to pick up a negative I1 times 6. Now we know what I1 is. I1 is 1.636 ampere. So VB minus VA is 8 minus 1.636 times 6. And that's going to give you minus 1.82 volts. And that solves the problem. Note that the negative answer here agrees with the fact that the potential here is smaller than the potential there because of the general flow of the direction of the current. Thank you for watching.